I'm Mark Weissman. I'm one of the co-organizers. Abhijit's not here tonight. I see a lot of new faces, so welcome. Who's here for the Stats Programming event for the first time? Show of hands. Okay, we're a little deviated from the norm, which is about half, but that's okay. Well, anyway, welcome. Really excited to have this event. It's been really busy the last few months, so that's why you haven't heard from us. We had the Hadley's talk back in September, which was phenomenal, and we filled up pretty much this room, which was pretty cool. Biggest event we've had in the history of Stats Programming DC and Data Community DC, so I was really excited about that. And we've got some stuff lined up for the next couple of months, so welcome. For those that don't know, and I'm sure many of you have seen this ad nauseum, but here it is again. Stats Programming DC is part of Data Community DC, and which is a broader organization in the DC area. We now have 8 different programs under our umbrella. They're all data science related in one way, data science related in one way or another. We started Data Community DC about 3.5 years ago, really to promote data and people that work with data in the DC area and their work. So we've had the 6 groups, Data Science DC, which deals more with like algorithms and techniques, sort of at a higher level. Data Innovation DC deals with the business of data. Data Education DC offers workshops across, like, kind of intro-level workshops across different topics. Data Viz, self-explanatory. SPDC, that's us. We deal with the how. So we like to see code here. So whether you're doing R, you're doing Python, you're doing Julia, you're doing MATLAB, you're doing SAS, you're doing Excel. Punchline. So yeah, I mean, we are really about, or the focus of this group is really to sort of show people how to do stuff using all of these tools. So I'm really excited about tonight's presentation because we really haven't had we've had maybe 1 or 2 sort of more mathematical intended talks or less statistical talks, so really excited about that. Data Wranglers, of course, deals with everything that happens before you do any analysis. And our 2 newest programs are the little owl logo, which is DC Night Owls, now called Digital Nomads DC, and Women Data Scientists DC just joined our umbrella. So as you can see, we cover pretty much the entire spectrum. Most of the groups have pretty regular events. So if you're new to our group, just go to datacommunitydc.org, sign up to our newsletter, follow us on Facebook and Twitter. Also, there is a calendar where we list everything that's going on. Sorry. Okay, sponsors. Those yummy empanadas that you just had are thanks to our sponsors. And we are entirely a sponsor-run organization. All of the monies that we collect from sponsorships we use for all of our operational costs, which aren't many, but one of them, the biggest one, is for food and refreshments. We realize you're hungry after a day's worth of work, and we want to offer something that's a little bit nicer than pizza. But that costs money. So please support us. And Booz Allen Hamilton has been an organizational sponsor. They're sponsoring Data Community DC as a whole. Any Booz folks here tonight? Welcome. Yeah, I'm at Booz Allen as well. And then, of course, Revolution Analytics has been a long-term sponsor of this group ever since the beginning. Revolution they're now part of Microsoft. They basically took R, made an enterprise version of R, and added some features to it, and Microsoft acquired them about 6 months ago. So again, we're always looking for sponsor opportunities. Sponsorship gives you the ability to have your logo up here, gives us money to run our events, and also gives you access to our community. So please come talk to us if your organization is interested in sponsoring. And we're pretty flexible, so let me know. And of course, GW, which has been a long-term partner and letting us use their spaces here tonight, which is great. So we want you to talk. So this organization, anything that we do at Data Community DC, regardless of the meetup, is for you. So, you come to these events to learn something. And all the people that work in the organization, all the people that present, everyone here is really doing this on a volunteer basis, and it's for the community. So I ask you to please come talk to me if you have a topic that you want to present on. So this is just a laundry list of topics, but you know, if you have an interesting talk and you want to present it, you have an option to do it. So just come tell me and we'll put it on the calendar. It's as easy as that. And you know, it could be, when I started running this Numerical group, I did not know R, and I learned R in the early days just by coming to the event. So you learn, trust me, and I really hope that you give something back to the community. So we have, these are our tentative events on the right-hand side. On January, we might have a talk on our bioconductor. For those that don't know what that is, bioconductor is sort of a parallel ecosystem than CRAN for packages and tools and techniques that was developed really like in the life sciences sector, a lot of genomics, gene sequencing stuff, and there's a whole project called Bioconductor, and there's a fellow at NIH who does a lot of stuff for Bioconductor, so I'm trying to get him to talk. February, we are going to do lightning talks. Lightning talks are short talks, about 7 to 8 minutes long. We try to have about 6 or 7 or 8 talks in a single night. So, you know, if you have a topic that you want to give a short presentation on, you know, kind of something that's fast and sort of fun, come talk to me. I'm looking for folks to do a lightning talk that night. We were going to do lightning talks a few months ago, that didn't happen. So we have a few people that expressed interest, but if you have a talk or if you have an idea, just come talk to me. This is supposed to be fun. And also in terms of the presentations, we really can do this one of multiple ways. One is like a full-blown talk like this evening, which is about 45-minute talk with Q&A at the end. Maybe 2 short talks in an evening, about 20 minutes each roughly, or lightning talks, which are the shortest ones we do. So come talk to me if you're interested in giving it a lightning talk. Usually after our events, we go to Tonic, which is it's like 2 blocks away from here on 21st and G, hang out. So if you're interested in going, I don't know who's gonna go, so just sort of hang out here, and whoever goes, people just sort of go with the flow. We don't have a reservation, we just sort of go there and just hang out. All right, announcements. So this is your turn for announcements. Are you hiring? Are you looking? Do you have an interesting project going on, or anything related to data science, R, et cetera, et cetera, et cetera? Now's your turn to talk. Please keep it short, and the floor is yours.
Hi, well, my name is Mike Tedu, and I'm hosting a series of seminars working on some fundamental data statistical modeling, specifically like regressions, forecasting, just map making, and power regression. And I specifically tailored that for people who use R, so anyone that's interested, please come see me afterwards. Now, I understand that many of you have the doctorate degree, postdocs, and postgrads, but I know there's still some people who still want to go through some fundamentals of statistical modeling. So if you're one of those and you're really interested, come see me. Thanks.
My name is Mike Tedu, Association for the Advancement of Science. I'm looking for data visualization person. It's really Q3.js. It's actually for journalism and content role, but either look at me in the meetup list or just look on the science AAAS.org website.
If you make an announcement and you're looking for people or whatever, at the end of the event, just come and stand down here so attendees can come and find you. Yeah.
Hello, I'm Casey, web dev at Chief. I actually have no stats background, but my girlfriend is getting a doctorate, so I thought it might be good. We're actually hiring at Chief 2 Python backend devs. I think one is stats focused, but most based around like database development, and I think some Django too. I can get you the specifics if you're interested, or if you know someone's interested. Also, we are hosting Data Viz meetup on Thursday. We're well beyond capacity already, but we'll have a live stream of that too. If you have any questions about any of that, feel free to ask. Thanks.
And thanks to Casey, he's actually recording tonight's talk, so hopefully we'll see him at more events and we'll be able to post more of our stuff online for those folks that can make it. We've been talking about doing this. We don't really have a great infrastructure to do it, but thank you, really. Any other announcements?
Hi, my name is David. I work for an education nonprofit in Reston, and we have an opening for a business analyst in our product development department. I brought some copies of the job description with me today, so if you're interested, please see me afterwards. Thank you.
Good evening. My name is Nathan Teeter. I work at a polling and research group we're called Morning Council. And we're looking to expand our data science team and just our technical team in general. So if you like using R and you like data science, or you just like programming in R and not the data science part, come see me afterwards. I'd love to talk with you.
Hi, my name is Zach White. I work in data science at Labs, which is a tech and consulting company. We work with a mix of political and nonprofit clients and also corporate clients. If you're interested in learning more, we have some positions open. So talk to you.
Any other announcements? Yes, please.
Hi, I'm Jane Hartsfield. I have a PhD in applied math from Rice, and I've been out of the job market for about 5 years. Started data science certification stuff from Coursera. I have no idea what I want to do, but I've learned R programming, regression. I'm doing machine learning now. I think machine learning is totally cool. So I don't know. If you think there's a fit or have some ideas for me, see me.
Do you have a card?
I don't even have a
You need to
card.
get a card.
I mean, I'm just trying to figure out what I want to do. So,
Just a Post-it note.
I'll write you a post-it.
Post it on the event link, and somebody will reach out to you.
Okay.
We have to start giving out when, I've been to the Strata conference several times, and I didn't see it the last time I was there, but in earlier ones, they used to give out, you'd have your name tag, and they'd give out these little stickies that you could stick on your name tag, and you'd have people like with multiple stickies, and one of them was like, hire me, like Data Rockstar and things like that. So we have to start doing that over here, like have like a little hire me sticker or whatever. So, any other announcements? All right, well, on that note, so that's me and Abhijit, who can be here tonight. We're easy to find. Please get in touch with us. Please participate. Please suggest speakers. Please talk. Please sponsor. And on that note, I want to introduce James. Really excited about tonight's talk. As I was telling someone outside, I don't think we've really ever done, most of our talks, definitely always using R for something, so whether it's visualization, it's data munging, it's modeling. I don't think we've ever had something that's sort of like more definitely mathematically inclined or numerically inclined as tonight. So I'm really excited that James got voluntold to give the talk tonight. And so curious, who is an R user in this room? Okay, good. All right, so James, welcome, James. Thank you.
They both are. Oh, one of them. Good string. So, I got it. If I show the right, there we go. I'm worried I wouldn't show the right data.
Can you folks in the back here? Okay. Sound check? Good.
Good evening, everyone. Again, I'm James Howard. Thank you all for coming here tonight. I wear many different hats. Let me first introduce myself very briefly. I wear many different hats. I'm a consultant here in DC, but tonight the hat I'm wearing is adjunct assistant professor at UMUC, which makes me sound a lot more impressive than I actually am. Generally speaking, I'm a data scientist, math nerd, and public policy wonk. My undergraduate degree is in mathematics, do a lot of core mathematics. I have 2 graduate degrees, master's and doctorate in public policy. I've been hacking on R since the 90s, and been living and breathing it for at least a solid 10 years now. So there's that. I want to talk about scientific computing and numerical analysis. Normally when you hear the word scientific computing or numerical analysis, people are really talking about something like MATLAB or SciPy or Mathematica. You don't really see a lot of people trying to solve numerical problems with R. But R has a lot of advantages for doing this. One is it has a great ecosystem underneath it, which gives you all the statistical tools when you need them, and a great data management toolkit, which I realize is in Python, but I never bothered to learn Python, so I don't worry too much about that. And it's free. You do MATLAB. MATLAB costs something like $1,500 a license. Mathematica is equally expensive, but R gives you all this stuff for free. Numerical analysis is when you're solving mathematical problems for a good enough answer. When you sit down, when you took calculus and you sat down and tried to solve math problems there, you're working out to get a precise answer, where the correct answer at the end of the day was something like 3 pi plus 2. You remember this, right? And if you actually worked it out to whatever 3 applied plus 2 is, something like 11.26 something or another, you'd get points taken off because your professor was evil. Remember all this? Right. So when you're doing numerical analysis, though, you're looking for that answer that's good enough. This is something that can solve an engineering problem, where you need a good answer and you need an accurate answer. But an answer with infinite precision is worthless to you. You don't have the time or energy, and you can't actually implement an answer of infinite precision. Take, for example, how many people in here have 3D printers or played with a 3D printer? So these things typically have a print resolution of something like 1/100 of a millimeter normally, something like that. So imagine if you're trying to build a curve and then actually print that curve. If you model that curve with any greater resolution than you can print, you're just wasting cycles. So numerical analysis is one of those places where you can actually find an answer that's good enough, and then implement it somehow. So what we're going to do tonight, and I know that somebody posted a comment, I don't know if the person's here tonight, but somebody posted a comment on the meetup group asking if this was going to be an introduction to R, like R101, and then just a handful of small examples here. If you don't know R, and I saw most people's hands go up on the R question, you're going to be kind of lost here. But what we're going to do is we're going to give some linear algebra examples. And we're going to start with some basic vectors and matrices, just slice and grab it, but then we're going to move right into stuff people don't look at. We're going to do a little bit of interpolation, we're going to do a little bit of integration, and we're going to do some root finding. Now, in general, this is the kind of material that you would cover in an undergraduate class over about 9-12 weeks. And we're going to try to just touch on it very briefly over, what, 45 minutes? Is that what I got?
Yeah.
45 minutes. So the goal here is not that you can walk out of here and find some area under a curve with R, but you know where to look. Make sense? So, nobody actually wants to see a PowerPoint presentation, so let's bring up R and stuff. And the first thing I want to do is create a 3 vectors. Is that actually viewable? Do I need to blow this up some?
You probably want to blow it up a little bit.
How do I do that?
Maybe change it to a white background as opposed to.
Yeah.
But,
I have a question. What specific, are you using any specific packages?
I don't think I load any packages in this. This is all core R. But normally when you think of core R, you think of statistical. You think of linear regression and that sort of thing, or logistic
Go
regression, or
to
whatever.
appearance.
Appearance.
Yeah,
thank you.
third one, and then just up the font size and.
Oh, hey, I can do that. Does that look like that'll work?
Yeah,
No. Where's the white one? That's
that one works.
Yeah. The one called Eclipse will definitely do the job. Oh yeah, so everybody can see that, I take it. So we have 3 vectors. Or 2 vectors rather, u and v, and a variable x, which just includes a number 7. These numbers were not picked entirely at random, but it's been like 7 or 8 months since I threw this example together, so I don't remember where they came from, but it's not really important. If you want to add, actually I have the line ready here, so I can just cut and paste. If you take a vector and add a single scalar to it, it just adds it element-wise, right? Everybody knows this? And if you take 2 vectors of the same length and add them together, it adds element 1 plus element 1, and then element 2 plus element 2, and element 3 plus element 3. No surprises here, right? But then, and this is one of the things I think surprises people first, is something about element recycling. And this happens if you take a vector, 2 vectors of different length, and add them together. What it does is it starts laying one on top of the other, and it just reuses it again and again and again until it runs out of length. And if they're not an even multiple, you're going to get a warning. So if we do this, where I take a vector of 3 and add a vector of length 2 to it, add them together, it stops and says, you got a problem here, just want to make sure you know about it. But it did sit down and actually just add these together. It took the first elements and added them together, the second elements and added them together, and then we have a third element in the one vector. It goes back to the first element of the second vector, adds them, then goes, oh, I'm not out of elements yet, and then kind of throws up on it. But it does produce a result, and it is a result we would expect. Moving from here, we end up with matrices. Create a matrix with a matrix. You've probably seen these before, probably even done it. This is, of course, the numbers 1 through 9. If we add 1, it again does it element-wise, right? And if we had a vector of length, of the same length as there are columns, it adds each row to that vector as though that row were an independent vector. It does not do it column-wise, it does it row-wise. Now, the thing about this is, we already got used to that idea of element recycling when we're adding vectors of different length. The problem is there's no way to do that in any meaningful way with matrices. So if we do this, it should give us a wonderful error. No, in this case it gave us a warning, because what it does is it tries to do it element-wise. It treats each vector, each row separately, and then adds the vector to it, again, recycling through. This isn't the example it gives the error. From here, we start wanting to kind of like break apart. So this is just all basic linear algebra, basic linear math, right? You have matrices and vectors, you add them, you can multiply them, it works the same way as adding them, you can divide them, all that other stuff. That's not interesting yet. This is where things start to get interesting. We can take a matrix here, and in this case, matrix 1 through 6 as a 3x2 matrix. And we can start doing things like taking diagonalization of these matrices. And in this case, it gives us a vector, just a plain vector, of the diagonal elements. With a non-square matrix, it starts in this corner, in the upper left-hand corner, starts going down until it runs out of elements. If you actually have a square matrix, it's going to give you the principal diagonal. And this is using A again. At this point, we want to do some really neat stuff, like matrix multiplication. We have a special operator inside R. If we just use star, it's going to try to multiply things element-wise. If we wrap star in these percent symbols, it actually gives us true matrix multiplication. This is the result of multiplying A times B. And we can also have a cross product because we have a function called cross product. It's a function for outer product. This applies to vectors. This is the outer product of those two vectors we created initially, u and v. And if we take the same, oh, it's on the screen, the percent star percent with two vectors, and then remember, they're going to have to be of equal length for this to work, and multiply and use that on them, then we get the dot product of those two vectors. I presume it's actually 14. I didn't work it out by hand ahead of time. So now, if you've done a lot of matrix math, you're looking at this going, okay, there's all the fundamental tools. What I really want to be able to do is solve a matrix equation, ax plus b. So this is kind of your fundamental equation in all linear algebra. You guys remember this. And what you want to do is you have A, which is a known value. And you have B, which is a known value. And you want to solve for x. And if you remember how to do this, what you do is you go through and do row reduction across the whole matrix, and eventually you get, so if you have A here, B, you do row reduction. Eventually, in this last column, you'll end up with the solution of x when you have an identity matrix where A was, right? If we do this inside R, we have a simple tool that does this for us. It's called solve. So if we create this matrix, A, and these numbers were selected to get us a particular result. We take B, we just run solve, we get the value of x, such that AX equals B. Now, all those times you've run linear regression, done linear regression inside R, this is all it did. This is the underlying thing. And when you've done least squares, this is what it did. It was just all hidden from you by something like, first of all, you have a mountain of code around it. A lot of that is error checking, just to make sure you're not shooting yourself in the foot. You'll note we're not doing any error checking here because, I've tested all this before, I know this works. And I won't go through and do the whole example. This is, by the way, for who asked me about the packages. There's a matrix package. It does come with our standard, but you do have to load it separately. And inside that, we have LU decomposition. LU decomposition, you might recall, is where you take a matrix A and break it down into a lower triangular matrix times another triangular matrix. With a matrix that's kind of like this, and these are all zeros. Times something that looks like this. Right? And one of the reasons you do this is because if you're going to be running a regression or reducing something row echelon form many, many times, you can actually cheat and do this. It's a little bit faster when you're doing it multiple times. If you're only going to do it once, there's no advantage in doing this. With LU, you actually get a breakdown of what's going on inside this matrix, and you should actually get 3 versions of it. You should get L times P times U, where P is a permutation matrix, which shows how the rows have changed place. So that's kind of a quick introduction to doing linear algebra in R. When doing time-wise. One of the other things, and I think this is really awesome, we can also do linear interpolation with R. Going back to basic numerical analysis, one of the things we can do is we can do the Vandermonde matrix to find a full polynomial interpolation for any data set, provided we're willing to accept enough degrees in the polynomial. But let's start with linear first. We're going to do this example, because this really shows off where R does some neat stuff. So here, we're going to begin by taking x 1 through 10, and we're going to take y as log x. So we created y equals log x, and there are no surprises here. No, we don't have 0 in here because we can't take log of 0. And we're going to create a plot. And that's, let me pull that over a little bit so you can see it. These data points here, log x all the way through. It looks just like a log plot should. And use par, by the way, to tell R, don't mess with my plot, I'm going to lay some more stuff on it. So you'll see that a lot of times, but that's not really important. We can use a function called a proxfun. Anybody here ever coded in Lisp before? A couple of hands. And if you're familiar with R, you might be aware of the fact R sometimes thinks it's Lisp. What we're going to do is we're going to, yeah, well, you know. So what we're going to get out of a proxfun is actually not a result in the traditional sense. It's going to produce a new function for us. So when I do flog, giving it the same x and y, where x is 1 through 10 and y is log of x, flog now does not have a linear approximation. It has a function to generate a linear approximation. And we can actually take a look at what's going on inside there. It's a native method. And due to some quirks in its implementation, it relies on a specific environment. For instance, you cannot save this. But it turns out we can plot it. 1 through 10. We're going to lay the color blue right on top of it. Each of these lines, this line here is linear from here to here. And this is linear from here to here. This means that each of those circles we have a hard corner, but that's probably okay for our purpose, for most purposes, right? As it's exactly what you'd expect from a linear interpolation. But if we didn't want those hard corners, maybe we wanted a differentiable function, something differentiable and continuous, we could use a spline. And R, conveniently enough, gives us the cubic spline function, which, let's see on screen first, works exactly the same way. So we're going to create a different sequence, something that should give us something a little bit more interesting. And this is the beginning of a polynomial function. It's x squared plus 5x minus 3. And you can see the circles over there, the dots representing where the points we evaluated are. And then run this again. And if we run linfun with if we create linfun here with the linear approximation function, we're going to get, again, a series of lines. This is the same thing we just did, except with a different function. And we see those hard corners are particularly pronounced, especially right here. For some odd reason, I didn't think to change the name of the functions. We're going to recreate linfun with a cubic spline in it. And this time we're going to color it green. Now, it's probably a little hard to see, but at each of these points, this is smooth here. This is the advantage of using a spline function. When you do this, this is continuous and differentiable here, twice differentiable. And this is really handy if you need to do some sort of specialized evaluation with that function. You have a solid estimation of it. Now, I mentioned when I started with the interpolation section, van der Waals matrices and polynomial interpolation. I don't think this is built into R. I've looked and I can't find it. But that's okay, because I have a really nice implementation of it right here. Well, nice-ish. I'm going to just put this polynomial interp function in here. And using 3, and remember, this was a quadratic function that we put in here initially. So with a quadratic function, we'd want to only evaluate 3 points. These 3 points define a quadratic curve. 2 points define a line, 3 points define a quadratic curve, and so on. So take x, we evaluated at 3 points. This is the same y equals x squared plus 5x minus 3 that we just did. And if I run polyinterp on this, I should get back a vector. This vector, you'll note, is the order of the coefficient. It's the coefficients in reverse order. -3, 5, and then 1. The reason we produce these in reverse order is it simplifies the implementation of what's called Horner's algorithm, where we can then reevaluate it. This is a recursive implementation of Horner's method, right here, where we go through and we evaluate a polynomial at some value x. So the neat thing is, if at this point I take, for some odd reason I put the x values first. Somebody pick an x between -10 and 10. 1. 1 works great. Actually, I have to save that vector, and then z, put it in here. We run this here. 1, is that 3? Yeah, that looks like that's about 3 right there. So with polyinterp, and it's a simple van der Waals, as I said, it's a simple matrix, simple regression. It's like 6 lines of code. We actually get a quadratic curve described that we can plug into another function and evaluate. Now, from here, I'm going to talk about integration. Integration is actually about the easiest thing you can do in R. There's a function called integrate. You give it a function, you give it a lower bound and an upper bound. And with the same log, you get it along with an error estimation. Now at this point, it's kind of worth noting that when you installed R, one of the things it came with was a large library called linpack in Fortran. It is where most of these functions live. They're compiled code, they're Fortran code. They've also been around forever. They were initially released in the 70s. They've been revised a little bit here and there, but their core kind of remains the same. And for this integrate, it just goes out and calls that function. It has a little wrapper to make it think it's R-like, but in the end, nothing special is happening here except having Fortran do it. Going back to our F log, which is the approximation that's linear, the approximation that's cubic rather. We can run it as well. We can actually see how good the approximation is. When we go to find this area under the curve, we see it's accurate to 2 decimal places. There's a library called Gauss Quad, which exists, that also includes a number of other integration routines. There are reasons you might want to use different ones. The big one is that integrate expects finite limits. If you have something that's going to have an infinite limit, say for instance you want to integrate some function from 0 to infinity, or from minus infinity to infinity, or minus infinity to 0, or something like that, you need to use different functions. And there are a whole suite of those inside Gauss Quad that do that. I'm not going to demo any of those. I think I'm actually going through this a little bit faster than expected. I'm going through this a little bit faster than expected.
I have a question for you.
Yeah.
So this is actually the first time that I'm seeing some of these functions. But flog, so flog is the spline approximation.
Yes.
So it is a function. So it gets stored as a function.
Yes. Where did I create flog? Flog is actually the linear interpolation, is the linear approximation. But yeah, same idea. But yeah, that's stored as a function. We can take flog and evaluate it at any point. For instance, flog, what was it? 1 was the example we just used. And it gives it at 0. Maybe that's believable.
No, that's the logarithm.
Oh, that's a logarithm function. You're right. Hold on. Let's roll back. Flog of 1 is in fact 0. If you take flog, let's actually do 2.5 because we definitely know that's not going to be a correct answer. I don't know what the actual, anybody know what the log of, oh wait, I have a calculator here. Okay, that's not a bad approximation. And that's the nice thing about it. I mean, we have a linear thing that we can work with. Now, we all generally understand how logarithm function works and behaves. We can take an integral of it, we take derivatives of it. That's all pretty well documented in a calculus textbook. The idea here is that you want to use these sorts of tools when you have a function where you don't necessarily know how it behaves, or maybe say differentiating it or integrating it is something you really don't want to do by hand, and you don't have a license of Mathematica to deal with. Now, that's one set of instances where you'd want to use this. Another set of instances where you'd want to use this is if you just have a data set. If you just have a bunch of data points on a curve, say for instance a time series that you downloaded from the Fed, you might want to look at that and say, I need to integrate the area under this curve, but I don't even know what the equation is for this curve. Take the data points, you can approximate it with either a linear approximation or a spline function or any of a dozen other tools. Take that, integrate that, and you have a reasonable approximation. Now, each of these steps introduces error into this process. But as I said, normally, you can tolerate some degree of error. That's where these things really come in handy. The last kind of section here, because there really isn't a lot to integration, is root finding. Now, we're going to play with this function x squared plus x minus 6. X squared plus x minus 6. Remember mathematics. I'm sorry?
X minus 3 multiplied by x. That's 2.
Forgive me for the signs go. Plus 3. Okay? So we know where the roots are. There's going to be one real root at 2 and one at minus 3. So we create a function, f, and this f just implements this quadratic function. And then we're going to plot that again. And we have a nice, pretty curve. Let's put axes on this, and we can see where it's hitting the curve, or where it's hitting the x-axis in particular, because that's where real roots are. We can use this function called uniroot to find out where the root is. I'm going to run it and then explain what happened. First, we have an example. Where is it? We found something that's almost minus 3. It's actually not a bad estimate, is it? What's happening with uniroot is you give it first your function, and then the second argument is a vector of 2, well, it's a vector of more than one element, but 2 is sufficient, where you have some value where if you evaluate f at that function, it's negative, and another value where if you evaluate it, it's positive. And at this point, it plays the hot or colder game essentially with these numbers. It looks at it, it cuts the distance in half, and checks if it's positive or negative. Figures out if it's positive and the lower bound is negative, it knows that the root is somewhere between them. If it's positive, excuse me, if it's negative and that lower bound is negative, the lower bound should always be negative, then it knows there's no, well, there may be a root between them. It doesn't know, but it definitely knows that there's a root between the negative value and the other one, which is positive. And it keeps doing this and just narrows down, narrows down, narrows down until it reduces the distance between x min and x max in those bounds. When it does that, it never actually finds a root. All it does is it knows there's a root within some small degree. And it goes ahead and returns some value within there, usually the midpoint. So that's how uniroot works. And in fact, this is one where it's worth showing the page. You give the integral that sets the lower based on this. The other thing you can do is you can actually give it also explicit estimates of what the function values are at those values of x. There are other methods for finding roots, specifically Newton's method and the secant method, which work differently. They don't require knowing that positive negative boundary point, but this is the method that's built into R. Lastly, I'll show this example. I take Z. If I take Z and put a basic vector into it, this vector should correspond to these values, -6, 1, and 1. We're describing again the coefficients of this polynomial. There's a function called polyroot, which will find all of the roots. We'll also find imaginary roots, as you can see. In this case, they're both real. And then down here at the bottom is Horner's method, which I've already demonstrated. The idea here is that you have a lot of rich tools underneath the statistical trappings of R to do a lot of really neat mathematical tricks. There's a lot more I haven't discussed. There's a lot more you can very quickly implement. That's one of the reasons I showed Horner's method and the polynomial interpolation routine. Those are each like 7 lines of code, and even with a little bit of error check, with adding a little bit of error checking, they'd be very production quality for a lot of purposes. This can solve a lot of the same problems you have where you might normally be using MATLAB or Python or even C to solve them. So I'm going to head back to the presentation for a minute. One of the big differences, though, you need to face with this is that R is notoriously slow. If you have a lot of experience with R, you know how slow it can be, especially when you're doing loops. It is much, much slower than MATLAB. And doing some speed trials with with linear regression a couple of years ago, we found that R took about 10 times longer than MATLAB did just to run some basic, row reductions. But one of the things I think is that R is certainly more inviting than MATLAB and Python in setting these things up. With MATLAB, you don't have a basic tool just to load in a data set like read CSV. You don't have a nice tool for interfacing with it like RStudio. You don't have a lot of the other trappings that people have used to make R really inviting for producing papers and that sort of thing. The other thing is R has a huge suite of tools in CRAN and Bioconductor and a number of others, which you can draw upon. So if you need to do something like finding an area under a curve dictated by some data set, it's pretty easy. Create the function, then you can run then you can run the integration routine over it, and then do whatever else you're going to do with it statistically. Two of the last things I want to mention is there are 2 really great books out there. Both of them are published by CRC Press. One is Victor A. Bloomfield's Using R for Numerical Analysis in Science and Engineering. The other is Scientific Programming and Simulation Using R by Jones, Naylor, and Robinson. Both of these are fantastic books. They include similar examples of these and many, many others. Routines on how to generate random numbers, routines on optimization, which I skipped over completely since we could spend 3 weeks on that, and some other things. Finally, this is where I get to plug things, right? Coming next year, it's why I don't have a title or a cover for it yet, is computational methods for numerical analysis with R, assuming I finish writing it. And this will actually not include how to do these things, but even lower, how to implement an LU decomposition function, how to implement row echelon form, how to implement an integration routine. So it has 50, 60 examples of code in it, along with how to use them, how they work, and that sort of thing. So that's my presentation. I hope there are questions. There's no way on earth there are no questions at this point.
I was wondering if you had anything on numerical regression testing in R.
Such as?
Recursive polynomials.
And not off the top of my head. Let's talk about that afterwards, because I think there's some interesting stuff there. But I've never worked with it before.
What is R-horn?
What is R-horn? Oh, it's the Horner method and it's recursive, so I prefaced it with R.
What is Horner?
Oh, so the Horner method is a way of evaluating.
I'm asking an iterative question.
Yes, it is an iterative question. Horner's method. Hold on, actually, let me show you a non-recursive version of Horner's method, and that might make a little bit more sense. Actually, this will make much more sense. So this is Horner's rule. And what you do is you walk over each of the coefficients in a polynomial. And as you walk through, first of all, you have a running total sum in your polynomial, of your polynomial value, which we're calling y here. This helps if I could point right here, which we're calling y right here. As we go through, we take that y value and multiply it by x, and then add the current coefficient. And then we do this from the bottom up, and by bottom up I mean smallest coefficient go on up. And if you think about it, if you started with, get a pen, so I'm going to have to keep track of what I'm doing here. 6, 1, or minus 6, 1, 1. You start at the very beginning, y should be 0, first time through the loop. Take that, x times y is still 0, add this first beta, you get minus 6. Come back through. This is an awful explanation for this. I think there's a good place to have a copy of it.
Isn't that similar to the Taylor function, like if that's the coefficient, you get the value of the coefficient?
Yeah, but I'm trying to figure out if I want to do the whole proof right now.
You don't have to.
So, but no, it's an expansion of a basic function. So if you take this is the same as x times x plus 1 minus 6. And this is what it's doing, except it's doing it for, an indeterminately large number of polynomials. So that's what that's going on there. The recursive version is because I wrote a recursive version because I like recursion. Too many years as an undergraduate CS major before I left from that. But no, I mean, this is a straight through version. I don't want to call it recursive. It's just a plain loop. And then right below here, we have a recursive version. There might be another one in here. Oh yeah, this is the obvious way to implement a polynomial based on a vector. So you go through and you step through the vector, take x to that power, and then multiply by the coefficient and keep a running sum. Right? Turns out this has all sorts of issues with it, but it's worth seeing how you would do it that way. And there might even be another one in here. Oh, here's a bit. This is a recursive. No, what is this one? Oh, this is one where we cache the values going through, so it saves some memory and some speed. But
can I put the function for you if you don't mind?
Yeah, go ahead.
Is it okay?
Please.
I'm sorry.
I mean, there are like 5 different ways in this file of calculating a polynomial. So.
For A0 plus A1 plus A2 x2 plus x plus was
Right.
K. So what happened was each one of them starts from the K, which is A, and then it will calculate the coefficient. So it will be -6, and then +1 and then +1. So it will be those coefficients. And it started from there, and then it will iterate.
Well, no, that's actually not quite right. Because what it really is here.
Sorry.
No, it's fine.
Sifters.
If you do this, this will make it clear. You have f of x equals beta 0 plus beta, parentheses, beta 1 times x, or plus x, times beta 2 plus x, parentheses, beta 3, and then plus, and then that goes on forever like that. So you end up with this infinite nesting series of betas and x's. So that's Horner's method, and it's it's one of those things where once you, it's really obvious once you, oh, okay, but there's no easy way to write it down because it's just this infinite nested series.
So this is for introduction purposes, using formulated equations.
Yeah.
Might work, but for people who work with real data, for us, would we be fitting a geom or some sort of regression-based techniques and figuring out a formula and then apply this kind of numerical analysis on top of it?
You could if you want to. And I've tried this before where I actually used, I need to find I had a data set, I ran a centered regression analysis on it. And then I need to take one of the and then I need to find the area under the curve using one of the coefficients, right? So I go through, I run the centered regression, I pulled out the coefficient I needed from the model, and then plugged it into a new function that looked kind of like that. But a little bit, I mean, it's a little bit different because it's also multinomial and all this other stuff. And then calculated used integrate to find the area under that curve. It worked well enough. And at the same time, I've also taken a live data set, and this is in the same project, taken a live data set when I need to figure out what somebody was using as a discount rate in a project so I could implement it again. They didn't document it. I used Uniroot to basically the same way you would use GoalSeek in Excel to figure out what the discount rate they used was so I could mirror it later in another project. So I mean, those are examples of where you could do this in an actual project. I'm trying to think of any other cases. I've never done an interpolation and then deployed it that way, like it's a live project. I've done it where I did it as a step in a project, but never like set it off to let it go on its own, if that makes sense.
I mean, sometimes if I have a custom function I want to optimize, I was wondering if there's probably asking for too much. A neat wrapper function, like, oh, here is my R object. I'm giving it to you by that's the point. So for some regression models, it might be easier for me to create that equation, but for other models, more of a hassle to actually complete. There's no real neat formula for certain cases.
No, there isn't. But you know, for doing optimization, that's gradient descent. It's one-dimensional, but it'll get the job done. I mean, you can extend it to multiple dimensions fairly easily. That's what I'm doing next week. So I just haven't gotten to it yet. This is reasonably effective. It gets me a result that's good enough. But yeah, I mean, if you need to, you know, this is one of the things that I often have trouble explaining to people is, you know, data science isn't something you can do on autopilot. When you're doing data science, you need to be able to take your data and understand it before you can run your analysis on it. Whether that is, you know, as you said, make a function out of it somehow, like using something like the spline fun or something else, before you can do that. I mean, it's a tool you have to babysit, not one you can just, not the first time anyway, let it go and do its thing.
No, I was wondering if you and packages that exist in our community are the packages that might help point into the right direction. that not be related?
I can think of like 12 you could use at once. So, and that's the other problem with R. So many things are developed by volunteers. They just create the piece they need. So yeah, I mean, send me an email with exactly what you're trying to do, and I'll walk through it. Yeah, no, I know, I understand. It's yeah.
I want to use. I haven't done it yet. I want to use it for text mining. Like, you know, I heard that I'm trying to do text mining. I want to have a text file and where it has, for example, distribution, like how many words of distribution, how many words. So how difficult to use this software to use the text mining?
Mark, you actually have experience with this, right?
Some. There is a whole package called TM, which is called text mining, and
they're great documentation. I'm not a text mining expert. I've walked through the demos in TM quite successfully and mirrored the behavior of it. I've never.
Yeah,
but I'm not a text miner.
There is actually a lot of great documentation out there for TM, which walks you through like examples on how to take a body of text, how to clean it up, how to stem it, lem it, etc. How to build your TF-IDF and how to do whatever it is. I mean, it's got a lot of capability to it. I think that's pretty much the workhorse for text mining in R right now.
Okay. So if you download the basic R, do you have to add another package for text mining package?
So TM is something that you have to install separately. Base R, when you install R, you get, when you start R,
right.
It loads the base package, and there's like 8 or 9 packages that aren't necessarily loaded at the time, but are available in your base installation. All of these things are extra that you would have to go to CRAN and install it separately.
But they're free.
Yeah.
And I'm a huge fan, in all seriousness, of RStudio. And inside RStudio, you just click right here under Install under Packages, and you can. I'm not connected to the internet, so it won't. I just type TM, and it'll come down over the next 30 seconds or so and install it. Along with most of the rest of these others. And it's funny I should mention this because there's there's a package for splines that you can get. There's a function for, where's the other one? There's what else? There's Gauss plot. Another one I wanted to show you. And one of the other nice things is if you're crazy enough, you can actually install R with a high-speed implementation of the linear algebra routines called Atlas, which is available. I've never actually successfully done this. I have been able to install it using a pre-compiled version of Atlas. I've never been able to build Atlas from scratch and make it work. But it is something you can theoretically do.
Talk about integration for a little bit. And you were talking about a one-dimensional case, but if for some reason you needed to integrate some function in multiple dimensions, obviously in some ways that's similar to the kind of problems that you would like to solve in Monte Carlo methods in Bayesian analysis. So I'm wondering, is there kind of overlap between the numerical methods that people have built for Bayesian analysis and what's potentially?
Absolutely, yes. And just for fun, here's a two-dimensional version of Monte Carlo integration. Monte Carlo. So normally when you do numerical integration, it mirrors the definition of integration. So you have something like this. You have a curve. You want to find the area from say here to here. You take this and you build little tiny rectangles, and then you sum up their areas. And if you'll recall from the definition of the integral is what happens when you compress the rectangle's width to approximately 0, and then you get the sum, right? So with numerical integration, the base case Newton Cotes method, called midpoint rule, does this, for the rectangle rule, does this, except you can't practically compress that space to 0. So you just compress it small enough, you get an answer you like. And then the way integrate itself works inside R is it uses a function called Q something or another inside linpack. And that function itself is an adaptive routine, where what it does is it takes this, which is just a linear interpolation between these 2 points, and then takes one which is also a quadratic interpolation between those 2 points. We know very easily how to calculate a linear interpolation, since that's a trapezoid, and how to also calculate an integral for a quadratic function. What we do is we calculate both, check the difference. If the difference is very, very, very small, then we believe we're very close with both estimates, and then we pick one and then move on. These methods blow up past 1 dimension. They just become excessively error-prone past 1 dimension. And at that point, you're best off just doing Monte Carlo integration. This is a 2-dimensional Monte Carlo integrator right here. It is not particularly exciting, and it is also error-prone because I didn't put that much work into it. But that's because it's an example function, not meant to have for actual production use. But you can extend this out as far as you want to dimensionalize. Oh, sorry, I didn't see your hand.
I guess you said you weren't going to talk about optimization, but if you were to talk about it.
Well, I started to when I showed the gradient descent function.
However, R usually maximizes a likelihood function or something like that. Are the defaults generally good enough, or is it worthwhile to pop them and try to do things like this?
Okay, so you're going to love this answer. 1, I'd never taken apart the MLE estimator inside R. 2, my experience with it is it's always been good enough for me. 3, it's absolutely worth taking it apart and seeing what's going on inside there, because you never know. I mean, I've seen examples where somebody who didn't have a numerical background, an economist in particular, was doing an analysis, and it goes like, this result, why is it my colleague runs the same identical function, this was in MATLAB, identical function in MATLAB, and gets very different results from me. I take one look at it, it's doing these really tiny divisions with really small numbers. One guy's doing it on a 64-bit computer, one guy's doing it on a 32-bit computer. He had no idea about numerical error. You never know what's going to happen when you start tearing apart the function and seeing where things can go wrong, because you don't necessarily know how it's implemented until you do. So that's kind of part of the point of this discussion, is saying this is what's underneath. Look for it when you can. Anything else? Thank you, everyone.
Any website or any URL you would recommend right now that's available specifically for mathematical?
So that's hard. They're the 2 books I showed covers of, which aren't websites, obviously.
Do they have, because sometimes the books have code associated with it?
Yeah, I don't. Bloomfield does not. I don't know about the other one. You can go to the Revolution Analytics blog. They've been doing some stuff with interpolation lately because somebody there discovered it and thinks it's cool. I'm in the middle of putting together a website to go along with the book I'm writing, and I have a massive package of all these, and you can see all the functions over here. They're currently in it.
Yeah.
I just haven't released it yet. That's coming probably right after the beginning of the year.
Let me show you a resource.
Go ahead.
I don't know if there's anything in there, but.
You want a web browser?
No,
Oh, they don't have a browser.
I can go here.
Go ahead. At home. And then computer.
So if you, for those that you don't know, first you can go to this called CRAN task views, right? And for those that use R, you know that CRAN is the repository. So if you look at, there's these things called task views, which break apart package listings by functional area. So here's one that's called numerical mathematics.
Oh, I didn't even think about that.
Yeah, so here would be listed probably a lot of the packages that he talked about. Again, these are just the package. I personally, I haven't seen a lot of, most of the time when people do stuff in R and post stuff on it, it's really doing, data manipulation, data visualization, or some sort of statistical modeling or machine learning. I haven't seen a lot of blogs or just sort of examples dedicated to numerical analysis or numerical computations with R, which is why I'm actually glad we're having this discussion tonight.
I will say this, and since I've got this list in front of me here, like SVD, for instance, is the underlying mechanism behind support vector machines.
Well, that's singular value decomposition.
Yes. Let's see here. And then, I still have nightmares about eigenvalues from linear algebra, and there's a whole package for doing that. There's a package here on optimization, optar.
Well, there's a whole task suite just on optimization here.
Yeah, there's that too.
So this is probably a great resource to just understand what packages are out there. Now, granted, some of the packages, some of them may already have a vignette written, which is just a more explicit example on how to do it. If you download the documentation itself, which is the functions and the parameters, that doesn't tell you. That just tells you what the function is doing. It doesn't tell you what to do with the function. Some vignette, there are very well written vignettes. There are vignettes, but again, I just think this just occurred to me. This is probably a good place to start. So, and go to Stack Overflow, which is probably another great resource just to. I mean, let's face it, right? What would we do today without Google and Stack Overflow and all this stuff? I mean, none of us would be data scientists.
I recently heard a joke that they're going to rename the major of computer science to Google and Stack Overflow.
I wouldn't. But yeah, because I mean, to his point, a lot of the stuff that's happening under the hood when you're doing machine learning is optimization, and optimization is numerical computing. So it's all related.
Somebody could spend an entire night in here on optimization. Somebody could spend an entire 6 weeks in here on optimization.
They could probably get done in 5.
Yeah.
Do you have favorite quick guides for both basic commands and for the built-in functions, plotting, and so on? I mean, maybe you have it all memorized.
Just about any book you pick up will have that introductory guide in it. It's kind of a prereq for an R book to have that first 2-3 chapters. Oh, here's how you use R.
I mean, a summary quick guide.
Yeah, I'm thinking that Introductory Statistics with R by Peter Dahlgaard is an excellent example.
My personal favorite book in terms of introduction to R stuff or introductory level R is this one, The Art of R Computing by Norm Matloff. Yes. And there's a relatively good one that I found recently, which is it's the Manning Practical R.
Wait, was that one available for free?
Probably.
Okay.
No, it's not. I mean, well, this is probably just a paper.
Oh, okay.
If you Google enough, you might find it somewhere.
That's a questionable legality.
Don't this one here, Practical Data Science R, I've been using this one in the class that I'm teaching now, and I like it. I think it explains a lot of the concepts pretty well. And again, this is probably one of my favorite ones, The Art of R Programming. It has been for some time.
I second that.
Which one? Art of R?
This Art of R Programming.
Yeah.
I really like it.
There's a whole bunch of R books, and Jared's book is actually pretty good. Jared Lander's book. For everyone. So this one, yeah.
Are you familiar with the R journal?
I think so.
It's
oh wait.
It's really good. It's really like.
Yeah, but that doesn't do very good at being an introductory.
No, yeah. And do they? I don't know how often they publish.
Don't underestimate the Coursera class on R, the John Hopkins one.
Yeah, the Hopkins course, it's free.
That is stellar. I mean, for introducing people to basics.
I would also suggest that the R cookbook by Peter Teeter.
That's right. Yeah.
Is a magnificent quick reference on how to do X, Y, or Z really fast.
Right, because it is a cookbook. Like you look up a specific. It's broken down by examples, like how to add a title to a graph. So it tells you. Like it's a cookbook. It's a recipe-driven book. That's a really good.
And that's something I have to look up every time I do it.
The Johns Hopkins course has a lead pub book because
Cool.
Oh. You can get it from lead pub and you can get it for $0 if you want to do that. We have suggested price. $10 or $15 once you get it for $0.
And just on the practical data science zoom in. There's an accompanying video course on Udemy that you can get for whatever promotion you have. And you can
This one actually, so the Manning book has actually a whole GitHub repo associated with it. There are errors in the code.
I'm sure there are errors in my code.
Yeah, but I like how it's broken down. So again, I've been using that in a class I'm teaching at Mason this semester, and it's been working out pretty well. So those are probably the 3 or 4 top things that, at least to me, come to mind. I don't know what else comes to mind.
There's also a free edX class that's it's between edX, Microsoft, and DataCamp, and it's
Oh, that's right. The
data R.
So for online stuff, the DataCamp guys have put together like a really cool intro to R. These are interactive, so these are videos.
But there's even an enhanced one on edX that it sort of makes it's I think DAT204X is what it's called, and yeah, so they did that with.
I have not seen this.
Yeah, this is new to me.
Yeah. But I met the DataCamp guys a few months ago. They were here, I think in October when we had the Data Science for Education event, and I had a chance to talk to them a lot. And I think what they're doing is actually pretty cool. And using this platform, you can do like coding exercises as you're learning this stuff. And their subscription right now is pretty much ridiculous. I mean, it's $25 a month for unlimited access. It sort of pay as you go. I don't think you can get any better than that. But I think the content is.
for students.
I'm sorry?
It's cheaper for students. If there are any students here. The data camp.
Is there ones for students?
Apparently there's a discount.
Oh, I guess so. I don't know. I haven't looked at it, but
everybody sells their old student ID, right? I only graduated last year, so I can say that.
Or you teach.
Right, yeah, I have to do that too.
But yeah, I really like what these guys are doing with sort of the introductory stuff with R.
So here's a dumb question. So sometimes when you're doing I/O, you're changing directories. Is there a command in R that will tell me which directory you're at?
Get WD.
Thank you.
Get working directory.
Yes.
This is a little off topic from this lecture, but I'm curious, you said you're a public policy monk?
Sure.
And
don't get him started.
And you live and breathe R. So how do you use R in public policy?
That's a juicy problem. So as I just alluded to, I graduated last year. My dissertation was actually an R file that generated LaTeX, that generated PDFs by loading in a whole ton of data about flood insurance, analyzing it about 75 different ways, dumping graphs, dumping out analyses, dumping out Monte Carlo analyses, just dumping out huge amounts of data, producing a nice little PDF, which of course was then approved. And that's how I did that. I mean, it was a document that it took me 4 years, but I started it in R. I didn't start in Word or something. I started in R and just started having it do the things first. And much to the irritation of my advisor, I'm sure, because he's a Mathematica nerd, not an R nerd. But yeah, I mean and then whether it's that or in all honesty, the first thing I do when I'm doing any project, any new analysis for public policy work or whatever, first thing I do, create a directory, get an init, dump some data in there, dump an R file in there, which I always call load star for anyone old enough to get the reference, that does whatever prep work has to be done, and then start building an R file that works with SWeave and LaTeX and start having it generate stuff, and that's how I do it. That's how I do everything.
So
that's how I write letters to my mother.
So
Wait, haven't you heard?
If I visited your GitHub account, would I be able to?
No, because I don't share any of that. They're all private repos on Bitbucket. Okay. I'm trying to push more of the stuff over there. A lot has to do with the fact I'm dealing with a lot of data I can't share. Okay. And that's why that is. With a lot of the examples I showed in this, there is a packet. There's actually an empty space right now on GitHub, but I'm going to be pushing that package, I hope, fairly soon. That includes, like I said, probably 50 or 60 different algorithms for numerical analysis. I'm working on another paper right now where I can share the data. As soon as I get acceptance, someone will probably push it up there. So,
What will your package be called?
CMNA.
CMNA.
Computational Methods for Numerical Analysis is what it stands for. And if you go to jameshoward.us/CMNA, there will eventually be content there. Right now it's private, it's marked as private, but there will eventually be, because I just haven't taken the time to make it pretty yet. Yeah, I got problems. So, but yeah, that's where that'll.
If one thing, if you were to probably start writing a lot of which, something like you did in LaTeX, you probably wouldn't need to today because there's Markdown, R Markdown, which gives you a lot more flexibility and it's a lot more easier to use in learning LaTeX, which will translate your stuff to LaTeX, and you can embed LaTeX if you need to.
But now I'm old and set in my ways. So.
Well, you spent 4 years writing your own thing to do that. You're not going to go use something else.
No, and in fact, it turned out to be a huge advantage. My dissertation is actually going to be published by Springer here in a few months. And it took me, 6 hours total to convert it from a dissertation format to Springer format. Because, I had all the framework in place to make that transition. But that, cost me a year of work or so in the beginning. So, it's how you, prioritize things when you're doing that. The work you're going to have to do eventually, if you do it on the front end, you'll be a lot happier.
Like the front end.
Well, I meant like a front end of the project. But if you sink time at the beginning, we call it yak shaving. You know what I'm talking about. If you do, if you spend that time at the beginning, where you're like, oh, if I put all these things in order right now, I won't have to later. There actually is a fairly good payoff, assuming you're not just wasting time.
Any other questions? All right, folks, thanks for coming. Have a great evening. We'll see you in January. For those that made the announcements, if you're still around, just hang out over here.